Okay, so it started this topic of statistical inference in semester 3 as the last unit of statistics. We're going to continue the same unit as first unit of econometrics, and we're going to do section hypothesis testing in this. Now, let me try to make an attempt to develop intuition behind hypothesis testing. Okay, through an example. Let's say the government of India comes out with a new coin, and you toss a number of those coins, and you get this feeling that this coin is tail biased. Okay, now there's a difference. Tail here, I'm using the current word tail bias to mean that it's biased towards getting more tails, not in this sense, tail of a distribution. Okay, now let's say you want to prove this scientifically, statistically. How do you do that? The first thing would be you take a few coins and you toss them. Okay, step 1. And toss them and note down number of tails. Okay, or this is step 2. Note down, let's say, proportion of tails. How many tails have you got? Now what do you do? Step 3. Okay, now assuming that the coin is not biased and you make 100 tosses, one would expect the data to be something like this: 50, 60, 70, 80, 40, 30, 20. Okay, these are tails obtained in a toss of 100 coins. If the coin is not biased, if it's actually a fair coin, what would we expect? We would expect something like this. Okay. Okay. I've tried to make it look like a normal distribution. Okay. One would expect something like this. And on the vertical axis we would have the probability of obtaining like this. Okay, now more generally we can just label the axis not as actual but as proportion. So this would be .5, 0.6, 0.7, 0. 0.4, 0.3, 0.2. Okay, now the ideal circumstances, if we toss 100 coin, okay, we should get the proportion 0.5. But since this is a statistical experiment and then randomness, there is no certainty that we're going to end up here. Okay, but if we end up not here but here, do we say that the coin is necessarily biased? Okay, now any sane person, logical person would say that it's not necessarily to be here, but it's not all that weird to obtain 60 tails in a toss of 100. But what if you get here? Okay, let's say this is 60 tails in sample. Okay, so one may say fine, it's not 50, but we don't have enough evidence to say that this is tail biased. What if it turns out to be 80 tails in sample? Then things would start to look fishy. It's a little awkward to have a fair coin, toss it 100 times and get 80 tails out of those 100. Okay, now if we have to take a call on whether the coin is actually biased or not, and we get some figures from data, we necessarily have to draw a cutoff. Okay, maybe here, or even 75 would look a little weird. Maybe on 70. That till 70 fine. We don't have enough evidence, but if it's beyond 70, then things are fishy. Then we may infer. The keyword here is infer. We may infer that the coin is tail biased. It's biased towards getting more tails. This is the crux of hypothesis testing. Okay, the hypothesis here, roughly speaking, is whether the proportion of tails is equal to 0.5 or not, the true proportion. Okay, and the alternate here is one-tailed, because we are starting with the question is whether it's tail biased or not. Okay, so we're only going to look towards the right tail of this. Then we draw a cutoff, which is a critical value. If we take a sample and the value that we get for the proportion in the sample is towards the right of critical value, then we have evidence against null hypothesis. Okay, now let's get to terminology. Okay, and this is statistical inference. Nothing is ever proved. We only infer. The attempt that I am making here is, it's very easy to study this stuff, not do it for some time and forget it. Okay, the attempt here is that you should be able to remember this example, and through this example you should be able to remember this concept. Okay, so terminology. We have null hypothesis, okay, denoted as capital H with a subscript 0. In the particular example that we just took, if we denote theta as the true proportion of tails, on a number of tosses of the coin, this is to 0.5. Then we have an alternate hypothesis. In our particular example, the feeling that we started with, that the coin may be tail biased, so the true proportion of tails may be greater than 0.5. Okay. Now we're going to start by assuming that the true proportion is actually equal to 0.5. Okay. Now one can say that statisticians by and large are generally pessimistic. Okay. We're testing if the coin is actually biased. So what we're starting with, we're assuming that it's not biased. Okay. This will be every case of hypothesis testing. If we are looking for evidence for something, we're going to start with the assumption that it's not true. The other case is true. And then we're going to look for evidence. Okay. So null hypothesis here would be our target. We're going to target this. If this is not true, we're going to assume this is going to be true, and then we're going to target this with data. Okay. We have critical value, the cutoff that we just discussed, and going to have rejection region. If the value that the sample throws at us is more extreme than the critical value, okay, that more extreme region is the rejection region. It will be more clear with the example. Let's say in our particular example, he said that .5. Okay, H0 was theta is equal to 0.5 and H1 was theta is greater than 0.5. Okay. Then if it's one-tailed, we're going to have a critical value. Okay. Then this red one would be the rejection region. If this is one-tailed, okay. If this is two-tailed, then what would we do? We would just alter our null hypothesis by saying that this is not equal to 0.5. It can either be greater than or less than. Then now we're not testing the question that it's tail biased. Now this is checking for bias in general. Then what do we have? We would have two critical values. And two sections of the rejection region. Okay. Now, to have a firm grounding in this concept, let's start with an example. Okay, so the particular example that I'm taking is from medical sciences. Practically every profession there is would use statistics and statistical inference for operations. Okay, the question that we're looking is, so there's something called proximal humerus fractures in the elderly. Okay, we're not concerned with what it's called. Let's simply say problem in shoulder. This is something to do with issues in shoulder in the elderly. Okay, now in medicine there are two treatments for this issue. One is operative and the other one is through physio. Okay, so you have some data on this. Is this going fine? I think so. Okay, so we have data on 200 elderly people who've gone through treatment. 100 of them have gone through operative treatment and 100 have gone through physio only treatment. So we have total of 200 people. Okay, now the way we have managed this data is we've gotten clean figures on improvement and no improvement. Okay, now we're not concerned with what this is. Doctors would tell us what is considered as improvement and what is not improvement. Okay, after 6 months of the treatment. So the figures that we have is for operative procedures, 62 out of 100 patients showed improvement and 38 showed no improvement. And for physio only, 48 have shown improvement and 52 have not shown improvement. Okay, now different patients react differently to medical procedures, so there's a lot of randomness. Obviously, operative procedures are going to be a lot more expensive than physio only, and these are elderly. They don't want to get under the knife that easily. So, do we look at this data and say that there is evidence that the two are different? The outcome of the two procedures are different. Okay. Now, it's not something that we can simply say. Just like one example, data is slightly in favor of one may not statistically mean that they're different. For that, we'll use the concept of hypothesis testing. Now we've done one-tailed for the coin toss. Let's do two-tailed for this. Okay. So what we would take is theta in this would be the difference of proportion of patients which showed improvement. Let's say P sub 1 is the proportion of patients which showed improvement when they went through operative procedure, and P naught for physio only procedure. So theta would be then P1 minus P naught. Okay, this is theta. And if you are testing for differences in outcome, our null hypothesis would be going to start by assuming that there is no difference. So theta is 0. They're same in population. It's just the sample that is slightly different. If we're testing, if the question that we're testing is if there's any difference, then our alternative hypothesis becomes not equal to 0. It's just this. It's not just the sample, they're different in population as well. Okay. Now let's draw the density function for sample differences. Okay, this is for testing for population, but we're going to use sample for this purpose. Okay, now let's just remind you, although you already know this, theta would be parameter. This would be for population, this would be a statistic, and the general notation for statistics is we just put a caret on top of it. Okay. So, and we're going to draw this distribution by assuming that this is true. If this is true, then our expected value for sample difference should be 0. Okay. Now, I have just drawn this as a normal distribution, but I have not proved it till now how this would be a normal distribution. Okay, let's start with, okay, let me just tell you. Till the time we have such data, this is going to follow binomial. Okay, and statisticians love CLT. Okay, this was in the text that we referred, I think in the 4th chapter. Okay, the moment our data sample becomes large, binomial tends to normal. Okay, so we're just taking that approximation. So 100 is a large enough sample to have binomial becoming normal. Now find this would be 0. Now we also need variance for this. How do we get variance for this? Variance of this statistic would be variance of yes. Okay. and we're assuming that the two are uncorrelated. This is again an assumption that we're starting with. Variance of the proportion is P1 1 minus P1 by the sample size plus P0 1 minus P0 by sample size. This is for operative procedures, that is for physio only procedure. Okay, and I said that we're going to draw this distribution by assuming that the null hypothesis is true. If this is true, then the two are equal. Then we can simply do away with the subscripts in proportion. This would become P into 1 minus P into 1 by N1 plus 1 by N0. This would be the variance. Okay. Now, if we are drawing this normal, normal has two parameters, and we now have both of them. So we'll say that the distribution of this statistic follows normal distribution with parameters 0 and P1 minus P 1 by N1 plus 1 by N0. Okay. Now if we have these two, we can draw a normal distribution. We know where it's centered and we know how it's going to be spread out. Okay. The next thing that we need is we need to set what we call in statistics as the level of significance. Okay, so the area under this curve would be 1. It's a density function. Now what we need to select is, the aim here is to select critical value. And where do we get our critical values from? We get our critical values from level of significance. Okay, and statisticians love this to be 5%. There is no reason at all why this should be 5%. It's just a practice that we've gotten used to. Okay, in terms of ratio, this would be 0.05. And if we're doing a two-tailed test, so what we should have is, we should have our critical value positioned such that the area here and the area here, this should be 2.5%, 2.5%, together 5%. Okay, after choosing our level of significance and figuring out where our critical value should be positioned, this is the last thing. You select this point and this point as critical values. Okay, sequencing is very important. This should be in this very sequence. You figure out what your null hypothesis is, what your alternate hypothesis is, then you figure out the distribution. We say that this would follow binomial. If our sample is large enough, this is going to follow normal. Then we figure out what are the parameters of this distribution so that we can draw this distribution. It's normal, so we need to know where it's centered, what's the variance or standard distribution. Then we set our level of significance. If it's 5%, then we know for normal how this is going to be. It's going to be 2.5% in one tail, 2.5% in another tail. This would give us critical values after this procedure become residual. Okay. Now let me just make some space. As we studied in statistics, standardization is a tool which facilitates such analysis to a great extent. Okay. So now let's start studying the test statistic. What is test statistic? Test statistic is standardized form of this thing. Okay. Now if we have our sample statistic following normal distribution with all this, and let's say our test statistic t, this t is not this t, this t or this t, they are not related to the t distribution as of now. This t is only for t here, test statistic. Okay, you might as well use any other notation for that. The difference between capital and smaller would be, capital would say that smaller is actual calculated value and the capital is for distribution. Now let's standardize our sample statistic by dividing it by the standard error of itself. What would this be? This would be theta caret divided by standard is the square root of the variance of the distribution of sample statistic. This is what we have. Now if our sample statistic is centered on 0, our test statistic would also be centered on 0. This distribution will also be centered on 0. So what we would have is, we would have expected value of our test statistic also at 0. We need a distribution for this. Okay. Now we need variance of test statistic. I'm running out of space, so can we do, let me not rub this, let me use this small space for this. We need variance of t, which would be variance of p1 minus p1 by n1 plus 1 by n naught. This is just a constant. Okay, after you've calculated this, it becomes a constant. This is going to come out and it should be squared. So what we have is, we have p into 1 minus p to 1 by n1 plus 1 by n naught, and then variance of, okay, what is variance of this? This is this itself. So variance of our test statistic is 1. What we have with all this is, we have established that our test statistic which is the standardized form of our sample statistic. This our sample statistic was normally distributed, so our test statistic will also be normally distributed. Okay, with parameters expected value equal to 0 and variance is equal to 1. This is what we are trying to aim at. We were trying to get the standard normal distribution. After standardizing it, then this process becomes easy. Okay, so we can say now that our test statistic, let's get everything, make some space. Defined as this follows normal distribution with parameters 0 and 1. Okay, now not going to draw this again. I'm just going to say now this distribution is not for sample statistic. Now this distribution is for test statistic T, which is also centered on 0. Yeah. Now if this is not just another normal distribution, like if it was standard normal distribution, then what we can do, then it becomes very easy to find these critical values. We just look at the table, and we've done this so much time, so now we remember what is this going to be. It's going to be 1.96 and minus 1.96. Okay, now we already have data. Now this is ripe for testing. What do we do from here? We calculate the value of test statistic. How do we do that? We do that, and I do need space. How this is going to go away. Let the table remain. I'm doing this calculation with blue. The smaller case t would be for actual calculated value. And this calculated value now would come from the sample, so there will be a caret on top of everything now. We have these values from the sample. This is 0.62 minus 0.48. Okay, now at all times the distributions are being drawn assuming that the null was true. If the null was true, we're going to put 0.5 and 0.5 over here. Then we have 1 over 100 plus 1 over 100 squared. This is going to give us value 1.99. There's a point here. Okay, now after this calculation done, we're going to see where is this 1.99. It's slightly, just slightly to the right of our critical value. It's in the rejection region. Sorry, 1.99. Okay, and what you also need with this is you have to make up your mind. If it's 5%, it means 5%. That means it means 1.96. That means if it's 1.9625, you reject it. Okay. So what do? We reject this. We reject the null hypothesis that there is no difference between the two. Okay, then they're just different. Mind you, we have not proved at 5% level of significance that operative is better than physio. Not done that. We have just proved that they're different. This is what we aimed at doing. If we have to start with alternative hypothesis that this is better, it should be one-tailed, then it will be slightly different. Although I would claim here it's easier to do that. Once you have, you're going to get that, but till this moment we have strictly technically speaking not done that. They're just different. Okay. Now let's just get rid of all this. Okay. Although in the text the sequencing is slightly different, I'm going to discuss p-value immediately after this, and then power of the test and sample size later on. Okay, so now we're doing p-value. Now when we read p-value from the text, it's very confusing. Okay, I'm going to write it down so that we can read it a multiple times and then we'll relate it to whatever we have to do. The p-value is the probability calculated assuming that the null hypothesis is true. Okay, this is what we've been doing throughout. We're assuming that the null is true. And what are we calculating? We're calculating the probability of obtaining a value of the test statistic at least as contradictory to H naught as the value calculated available sample. Okay, looks like complicated hocus pocus. Okay, so let's just get back to what we've been doing. The same example, same null hypothesis. Null hypothesis was theta, the population parameter defined as differences in proportion of people showing improvement. This was going to be 0, and the alternate one was that they're not same. Difference is not 0. So this is still the distribution of test statistic. This was centered on 0. We have 1, we have 2 minus 1 minus 2. Okay. The calculated value of the test statistic was, we don't need this 2, okay, 1, this was 1.99. Okay. I'm going to use blue color now. Red I used for rejection region, critical value. And we also need now they should be same actually. Tails should be similar. Okay, so we're still doing a two-tailed analysis because our alternative hypothesis is such that. Now let's read this out. The p-value is the probability calculated assuming the null hypothesis is true. So this distribution is drawn assuming the null hypothesis is true. We're going to calculate the probability value of obtaining a value of the test statistics at least as contradictory to H0 as the value calculated from available sample. This is the value calculated from available sample. Now we need the probability of more values which are at least as contradictory. That means they are either contradictory to the same level or more contradictory. More contradictory would mean more away from this center. Okay, what is this probability? This probability can be obtained from the standard normal tables, and tell you the probability value here, p-value for t is equal to 1.99 is 0.047. Okay, so how do we calculate probability value for t? We know the distribution, and it's a standard distribution. There would be a standardized table for that. All we need to know is what is the probability of, what is the area to the right of this, and because it's standard normal combined, what is this area of having values less than minus 1.99 and more than 1.99. Okay, it's very easy, you should have known this. I'll just show you after this how to get this area for standard normal. Okay, you can get it for any value. It's very easy to know what is the value of area under the curve to the right of 1. Just have to look at the standard normal table. Alright, so does this hocus pocus now make sense? Okay, let me read it out again. 1/2 is calculated assuming that the null hypothesis is true. We concluded that part by saying that this distribution is drawn assuming null hypothesis is true, of obtaining the value of test statistic at least as contradictory. Okay, if it's far away from the center, it is contradictory to null hypothesis, at least as contradictory as the one calculated from the available sample. The probability value then is area in the extreme tails, which is the probability of getting more extreme values, or at least this one. This is what it is. Okay, now few basic rules. If your and say level of significance is denoted using alpha. Okay, the level of significance chosen in our previous example was 5%, so alpha was 0.05. Now if p-value is less than alpha, what do? We reject null hypothesis. And we shouldn't be saying we reject. You should say we have gathered enough evidence to infer that the null hypothesis is not true. This is the technically correct language of saying. Okay. Infer that null hypothesis is not true. And if p-value is greater than alpha, okay, then we say we fail to reject null hypothesis. We fail to say that this is not true. Okay, you never say that you accept this. You just say you fail to reject it. You don't have enough evidence to be able to reject it. These are technically correct lines in statistics. Okay, now if p-value is less than alpha, what do we have? We have the critical value to the left. Our critical was 1.96. The red area should be, the red one should be 0.025. The blue one is, red is half of 0.5, blue would be half of 0.47, then this is definitely going to be less than red. You also see that the diagram, you can calculate 0.047 divided by 2. If this is the case, then you know if p-value is less than alpha, you already know that the value of the test statistics that you have, it falls in the rejection region. Okay, it's the same analysis presented in two separate ways. Okay, any questions till here? Make sense? Now let's move forward. Power of the test and sample size. First I'll define what do we mean by power of the test, and then how is it related to the sample size. Okay, let me first create a sort of table. if we have a hypothesis, in reality either is going to be true or is going to be false. It's a different matter that we use technically correct language after analysis. We don't say it's true, we just say we fail to prove that it's false. Okay. If we're doing our analysis, we're going to, this is the actual case, what would be here, what we would end up doing. Either we would reject H naught or we fail to reject H naught. Okay. This, I would say, is a good outcome. This is true and we fail to reject it. This is how it should be. And if it's false, we should reject it. These are where we should be. But these are where we can accidentally be. And what we're doing, okay, let me just draw this. Critical value, critical value. The red one is the rejection region. Here also it's rejection region. Critical value. Critical value. Okay. Now, if H naught is true and we get the value calculated from the sample, this is where it's entered in this. Okay, we just say we fail to reject it, which is fine, and the area, this area, what is it? It's 1 minus alpha, because level of significance is alpha, and we said that that should be area under the curve to the extreme side, to the right of critical value, to the left. So remaining becomes 1 minus alpha. So the probability of failing to reject H naught when it's actually true is, we get our value here, that is 1 minus alpha. Okay. If it's true, either we reject it or we fail to reject it. This is going to be alpha. Alright. Now, if it's true and we are rejecting it, we are making an error. Statistics, this is type 1 error. Alright. If, and I'll explain after this slide how we actually get beta. Okay, but now I'll just say, if H naught is false and we still fail to reject it, that probability would be beta. Okay, and if H naught is false and we reject it, there's only two things we can do if it's false. If this is beta, this has to be 1 minus beta. Where's the error here? The error now is this. It's false, but we're not able to reject it. This is type 2 error. Okay, now I'll tell you a basic rule. Okay, a funny example how to memorize this. This is going to go into recording. If anyone makes complaint, I'll just mute this section so it disappears from the class. So let's say a girl goes to approaches a boy and says, I'm in love with you, and she's speaking the truth, and the boy says, I do not believe you. The boy is making a type 1 error. Hypothesis is true, he is rejecting it. So rejecting a true hypothesis is type 1 error. You can, whenever you forget it, you just think of the boy. The boy is making type 1 error. Okay, let's say he's a clever lad. The girl comes and says, I love you. Boy says, oh, I was not able to tell you, but I also love you. And he doesn't. He's just playing around. Now, if the girl accepts it, she's making a type 2 error. She's failing to reject. In this case, accept, but statistically speaking, she is failing to reject a false hypothesis. Remember this, you will never forget what type 1 error is, type 2 error. Remember the story and say, to begin with, the boy is making type 1 error. To ending it, the girl is making a type 2 error. If anyone makes a complaint in this video, this section will be muted out. One has to be very careful with these examples these days. Okay. Now, let's move on to how we calculate beta. Beta comes into play when our null is false. Throughout our thing, now let's do this with blue. This distribution is drawn assuming the null is true with black color. Okay. If indeed the null is false, that means there's no problem with the shape. The problem is where it's centered. It said, continuing with the same example, we have said that there is no difference. So theta, defined as the difference between the proportion of people showing improvement in the examples, there is no difference, so this is true. If indeed, let's say that this is false, there is actually some difference, that there would be some value of that difference over here. Now, let's say that is delta. Okay, there's no problem with the shape. So what we would have is the true distribution would be this. The problem would be where the distribution is centered. Okay, if the actual value of the parameter is theta and the distribution is this, and we collect a sample, there is a much higher probability that the test statistic would have a value somewhere close to delta. Okay, say this was our critical value and to the right the rejection region. This is our procedure. Ideally, then the value calculated using the sample should lie here, somewhere close to here, and we should be able to reject H naught. But samples being samples, they are random. We have this distribution. The distribution says this fact that there is a low probability, but there is that even though this may be true, the sample value may come somewhere over here. This is not touching the axis. If that is true and we get our value to the left of critical region, okay, red here does not mean region of rejection now. It has a different interpretation. It's just that this is false, this is true, but our sample is extreme, even though this is true and the value ends up being here. we would fail to reject it. Okay. And what we're doing is then we're making a type 2 error. This area is beta. The probability of values ending up here, even though this is true, that is beta. Area under this true density curve now. Type 2 error, it's false. Ideally, the value should be away, close to here, away from here, but things are not always ideal. It ends up here, we fail to reject it. Okay, that is beta, that is type 2 error. If things go well, we should have our value close to here. Further away there causes no problem. That is, if this is beta, this blue one is 1 minus beta. This is power of the test. 1 minus beta is the power of the test. 1 minus alpha is level of significance. Okay, the context is very different between level of significance and power of the test. You have to just remember the diagrams. Power of the test comes into play if null is false. If null is false, we have two distributions. The false one, which we have drawn assuming null as true, and a true one, which we do not know. Then we have power of the test coming into play and type 2 error. Otherwise, for level of significance, we don't have a distribution there. The red one is not there. This is the true one. And just by chance, your sample throws a value which is, let me just draw that one also. This diagram, when H naught is false, this one, only one distribution when it is true. In our example, this would be on eta, critical value, critical value, critical, critical. Okay. It may be so that this is true, fine, there's no problem, and just by chance you get a value here, and you say that now we have enough evidence in rejected. Although this is true, but just by chance you get there. Okay, so you can be sure this area is 1 minus alpha. That is the probability 1 minus alpha that you're going to fail to reject it when it's true. But again, now I'm not going to use red, I'm just going to say it. This small area alpha is the probability that you're going to end up rejecting a true hypothesis, type 1 error. Okay. Now, how does power of the test increase? How can we increase, or naturally, how does power of the test increase? If somehow naturally this is far away from whatever we have assumed is null. If we are assuming that there is no difference, if the actual difference is quite large, then power of the test would increase. Why so? Because the more, if you just push it there, okay, critical value is for the black one, it's fixed, it doesn't depend on red, doesn't depend on the true distribution, it depends on the false one. If we push, or if naturally, if it so happens that this is to the right, the red one would be to the right, black is there, the area under the red curve to the left of critical value, that would fall, and the remaining 1 minus beta, it would increase, that would increase the power of the test. Okay, that's one. Two, if the sample size increases, then what would happen? The variance would fall. See, n was in the denominator while calculating. We would have, let's say, we take the exact theta, I hope it's coming in the recording.